Hello everybody, my name is Daniele Sierragusano, image engineer at Filmlight. Welcome to this short video tutorial about the new improvements in Truelight color spaces introduced by Baselight version 5.0. This video focuses on the architectural changes of the color management, not on the new color space aware creative tools, which themselves highly rely on color management to achieve their goals. So the improvements are a new concept called the mastering color space. We have enlarged DRTs to DRT families and have introduced viewing conditions. In V5 we will ship a new default working color space called Filmlight T-Log eGamut, and we have worked on a new display rendering transform family called Truelight Cam, or short TCam. In addition to TCam, we will introduce a new concept or approach to looks or pleasing color reproduction called Truelight Scene Looks. Okay, let's jump directly into it. The first concept we will look at is the mastering color space. First, I explain the problem we are trying to solve. The problem comes with floating point color grading because floating point processing does not impose any practical numerical limitation and can achieve values below 0 and above 1. So there is not really any restriction in the viewing pipeline compared to integer-based or LUT-based systems. In addition to that, modern delivery color space container like Rec 2020 or DCI XYZ are wider in color gamut as the actual display technology in use for grading. The other way around, you could say, the color space achievable by the display is smaller than the delivery color space. With a floating point color grading system, there is no mechanism in place to actually allow us to limit the final render to the smaller display color space. So we are at risk to produce colors in the final delivery the colorist never saw while grading. In addition to those problems, we want to address the white point handling and chromatic adaptation transformation in Baselight, because in 4.4 and 1 the white point handling was kind of unintuitive. Okay, I have outlined our two typical color pipelines in Baselight. We have two kinds of schools in Baselight. We have the telecine style colorist and film style or scene referred style colorist. And we will see that the mastering color space is important for all the different types of grading styles. We have here different input color spaces and we convert them to a working color space. We apply the grade and we eventually have the data in the state of the grade result color space. In the case of telecine style, we directly convert from the grade result color space to the cursor or render color space. For simplicity, I named them here output color space. In the case for scene referred workflows, we use DRTs to convert the output color space to introduce some form of color appearance modeling and preferred color reproduction. As we can see, there is literally no instance that allows us to limit the output to a certain color volume of achievable colors. And this is what the mastering color space does. You can think of the mastering color space as a color volume limiter at the end of the color pipeline that limits the colors to a certain color volume or color range. This assures that nothing unseen by the colorist gets encoded in the hard copy delivery master. And typically the mastering color space gamut is the actual display color space or the color volume the display is capable of showing. If we grade on a typical DCI projector, we know that it can show the P3 volume and probably not much more. But we are rendering at the end to DCI XYZ, which is a much wider color space. So the mastering color space set to DCI P3 reflects the actual mastering display and assures that nothing out of P3 gets encoded into DCI XYZ. At this stage, we also define the mastering white point or the visual white point. The white point gets back propagated all the way to the working space and therefore specifies the white point of the scene. In other words, the mastering white point defines what the neutral axis red equals green equals blue actually means visually. You could say it defines the visual white point. This mastering white point then will be reproduced on all of the deliveries, no matter what the technical white point of any given delivery might be. And we are doing this with a new chromatic adaptation transformation. So here are some examples. This image has a lot of impossible colors encoded out of the gamut of my display, in this case sRGB. You can see in the RGB values down here, we have huge negative values, for example, -6 in the blue channel. Those values obviously cannot be displayed on any display device. This becomes a bit more obvious if I switch the cursor to DCI 2.6 gamma XYZ, so all these colors are outside of the range of my display. If I would render them into a DCP, these code values, which were clipped by the projector, would be actually encoded into the final DCP, color values the colorist never saw while grading. This becomes very obvious if we look into HDR, where we might want to use a 10,000 nit container with Rec 2020 primaries, but the display is only capable of showing a P3 gamut up to 1000 nits. The solution is the mastering color space hidden in the advanced section of the color scene settings. Here I can choose a color space which acts as a limiter on the output. For example, if I choose Rec 1886 2.4 gamma Rec 709, Baselight will clip all out of gamut values so that there is no data outside of the Rec 709 volume, even if I convert to a larger color space. The tone curve is not really used because we calculate and apply the clipping in the linear domain. The important value you are picking is the gamut and the white point. You can set the white point to from mastering space, and then it will use the white point specified by the color space. If we switch to P3 D60, you can see that we limit to P3 D60. The second use case in the mastering color space is the white point handling. Let's desaturate the image to get a clear view on the neutral axis. Now red equals green equals blue. But what does red equals green equals blue actually visually mean? In typical workflows, the white point is dictated by the technical white point of the display, or it is referenced in a standard. But this can be a creative choice, or at least you want to explicitly define the white point. So for example, if we change the white point to D55, Baselight will alter the neutral axis so that it appears visually as D55. You can think of it as the visual white point. Here for D60, D65 or D93, or this greenish DCI white, which we strongly discourage to use. So let's put it back to D65. Baselight will maintain the white point on all your deliverables. For example, if I set my display color space to DCI XYZ, we can see that Baselight does the correct scaling to reflect my mastering white point on the DCI XYZ color space. And if we change this, it will be reflected in the output. So we have basically banished the creative white points from the display color space and put it as settings in the scene. So the next topic we are going to discuss is display transform families and viewing conditions. Multi-deliverable projects are getting more complex because the different display capabilities and properties vary a lot. For example, absolute peak luminance, flare, achievable color volume, and surround. All those properties together we call viewing conditions. So having the ability to only apply a single display rendering transform that brings you from scene referred state to all of the different display referred states becomes a bottleneck. The current situation in 4.4M1 is that the user needs to choose different DRTs depending on different output color spaces for the same scene manually. This is very error prone and annoying. Also, we can see that the list of DRTs would become very, very long over time. Therefore, in Baselight 5.0, we introduced the concept of DRT families. A DRT family is a collection or a group of DRTs which tries to produce the same visual appearance of an image for different viewing conditions. So now Baselight is aware of your viewing condition. We ship with some standard viewing conditions: 48 nits dark surround, 108 nits dark surround, 100 nits dim surround, 100 nits bright surround, etc. And of course, you can specify your own viewing conditions as well. So for example, DCI P3 and XYZ both belong to the viewing condition 48 nits dark surround, and HLG for 1000 nits and PQ on 1000 nits would both belong to the viewing condition 1000 nits dim surround. And for each viewing condition, we apply a different DRT. In addition to that, we also want to apply a different mastering color space for each viewing condition. For example, for 48 nits viewing condition, we want to limit all the output to 48 nits P3. But for the 1000 nit viewing condition, we want a different mastering color space that limits to 1000 nits P3. Additionally, we might want to change also the visual white point for each viewing condition, maybe D60 for cinema and D65 for television deliveries. That means for every viewing condition, we want to specify a certain display rendering transform, mastering color space, and mastering white point. This sounds horribly complicated for the user, right? Well, actually it is not, I hope. So let's have a look how this actually works. In the DRT settings, we can see two types of DRT icons. The one with a single S-curve icon indicates a legacy single DRT. In addition, we can see DRTs with a multiple S-curve icon. This icon indicates a modern DRT family. For example, the Truelight cam is one of those. Choosing this creates another dropdown which gives access to the different DRTs of that family. But in practice, we do not need to choose them manually because Baselight detects the required DRT based on our chosen cursor or render color space. And further, we do not need to set the mastering space and white point manually, but also set it to from DRT. In the DRT family, we store a sensible DRT, mastering space and mastering white point for each and every viewing condition. For example, we choose DCI P3 D60 on the cursor, Baselight will automatically use the 48 nits dark surround DRT, a mastering space of P3 D60 and also a D60 mastering white point. If we choose DCI P3 color space with the greenish, very unsensible DCI white point, Baselight also uses the 48 nits dark surround DRT, but will use a P3 D60 mastering space and white point, so that the resulting white point will be visually D60 and not green. And if we later render to DCI XYZ, the same DRT will be used and we limit the rendering to P3 and we shift the white point to accommodate the D60 visual white point. Let's see what's happened if we change the cursor color space to Rec 1886 2.4 Gamma Rec 709. Baselight now automatically uses the 100 nits dim surround DRT, which is different to the 48 nits dark surround, and changes the mastering space to Rec 709. Also, the mastering white point is changed to D65, which is a very common white point workflow. Now we change the cursor color space to Rec 2020 2.4 Gamma Rec 709. First, we see that the DRT is different. It's a 100 nits video white. This is a special DRT for wider gamuts. But also the mastering color space has changed to limit to P3 with a D65 white point. So the maximum allowed gamut will be a P3 gamut. Last but not least, we changed the cursor to Rec 2020 2084 PQ for 1000 nits HDR. Baselight will automatically apply the correct 1000 nits DRT and changes the mastering color space and white point P3 D65 1000 nits. As you can see, Baselight changes all the various settings only based on my selection of the cursor and render color space, because Baselight knows the viewing condition each color space belongs to. And as always, if you want to change any of those default settings, it is all customizable in a FL transform file specifying custom DRT families. I hope this illustrates that setting up a very complex pipeline with various mastering color spaces, DRTs, white points is as easy as telling Baselight what color space your eyes are looking at, and then the whole system will adapt to this. Also, I don't think I need to mention that all this is not done via lookup tables, but all the transformations are calculated and applied in one 32-bit floating point stitched shader executed in one go on the GPU in real time. In the initial release of Baselight V5, we are shipping with two DRT families, the Academy's RRT and our new Truelight Cam DRT, which is our new color appearance model. But we are closely working together with ARRI, Red and Sony because they are also developing their own DRT families at the moment. Once they are available, we will include them in our system. Okay, next topic. The new working color space Filmlight T-Log E-Gamut. And sorry for this horribly cluttered slide. In Baselight V5, we ship a new camera-agnostic working color space called T-Log E-Gamut. It is specifically designed for legacy, non-color space-aware color grading operators like film grade, video grade, U-shift, etc. In contrast, all new Filmlight's creative tools are color space aware and will operate in their own working space. So we hope that the working color space itself will play a minor role in the future, as all tools will operate in their own color space anyway. But at the moment, a great portion of tools are not color space aware. They expect the data to be in some sort of shape. In contrast, new requirements on the camera and display sides have different demands on a working color space, and T-Log eGamut tries to bridge the gap between those worlds. It is not a radical new designed color space or has any sort of scientific consideration. In contrast, we have taken empirically proven designs and have optimized them for the color grading application. The first and very important part is the tone curve, T-Log. As you can see, it follows a typical Signon style curve with an almost pure log section in the top part and a nice toe in the shadows, compressing noise to make the overall signal robust against various color, spatial and temporal filtering. We added a bit of headroom on the upper part, so we encode a bit more than 9 stops above 18% gray, which should be enough space to drive a 10,000 nit display, even if the data is clamped to the 0 to 1 range. In other words, if you have something in the stack that clamps the data, like a cube for example, you should have enough headroom to drive all of your modern deliveries. As a drawback, every stop gets fewer code values. I'll try to visualize this here. The x-axis is encoded in a pure log to the base of 2. I added lines for each stop and the 2 additional lines for diffuse white and 18% gray. And the y-axis are the code values in T-Log. What we can see is that putting more and more range between 0 and 1 reduces the code value space for each stop, and with T-Log we are at a critical precision level for color grading. It is roughly 70 code values in 10-bit per stop in the upper part. That's why we do not recommend using T-Log at all in a 10-bit environment. 12 bits or more are recommended. In Baselight, all calculations are done in 32-bit floating point, but caches can be stored in 16-bit half float, which is another limiting factor for precision, as encoding logarithmic data in floating point is numerically speaking very inefficient, and the inefficiency increases the further we go up the tone scale. So we have chosen the range so that the precision is high enough for 16-bit half float representation, so we do not get any visual bandings in the highlights if cached in 16-bit half float. You can think of the primary set as an enlarged generic display. We project from the white point through the corners of the typical displays 709 and P3 and have chosen a sensible primary on that hue. This should give us nicer hue stability when working with U-shifts, etc. And we made the primaries as small as possible, but keeping an eye on the extreme output of a typical cinema camera. We try to find a set of primaries so that all camera data ends up in gamut of the working space, because legacy operators do not handle negative values and out of gamut colors very well. This was empirically derived from 50 extreme saturated original camera data supplied by customers. As we can see, many cinema cameras produce very unsensible data under extreme light conditions. This forces us to have quite large working primaries, wider as we would like, which is not necessarily good for other applications like legacy RGB-based keying, etc. Also here we are facing limitations on both sides. So T-Log eGamut should not feel dramatically different to already existing working spaces, but things should be aligned better so that operations like U-shifts and keying are a bit more intuitive and comfortable. Truelight Cam is a new display rendering transform family. By the way, CAM stands for Color Appearance Model and not for camera. Obviously it is based on a fully parameterized human perception model. A nice property is that it is highly optimized for real-time GPU rendering. In Baselight, Truelight Cam is actually applied as a shader in 32-bit floating point and not as a pre-baked cube. This elicits greater precision and quality on the final image, especially in the shadows. In addition, because it is a formula-based model, we have a very robust inverse model. So going from display to scene state is very robust. As a side note, nothing has changed from a practical standpoint. Going inverse should be always avoided, if possible. As it is fully parameterized, it is fully adaptable to any viewing condition and display luminance level. The parameters are not intended to be used as creative controls, but rather allowing to control the adaptation from scene to a certain viewing condition. In the first release of Baselight, we ship with presets for all common SDR and HDR viewing conditions, so there is no need to dial in some numbers. In fact, in the first release of version 5, the UI to tweak the parameters will not be shipped, but will be shipped in a subsequent release down the line, allowing the user to tweak the parameter for certain viewing conditions. The most important design goal of TCAM is the absence of any creative or subjective look, sometimes called pleasing color reproduction. It does not impart any kind of look or taste. It should be as clean as possible. The only goal it has is to reproduce the image how we saw it on set, and then reproduce the final grade on various viewing conditions as good as possible. But pleasing color reproduction is a very important aspect of our viewing pipeline. Therefore, we need this concept of pleasing color reproduction in addition to the clean DRT to achieve the desired visual performance. This brings us to the last topic, Truelight scene looks. Truelight scene looks are looks applied on scene-referred color spaces, but they do not alter the scene-referred state. Then, together with the TCAM DRT, they produce a certain preferred color reproduction. Important is that they do not reduce dynamic range or limited data in any way to allow us to reproduce the image on any viewing condition, SDR and HDR. In the first release of Baselight, we ship with a handful of those looks. Some are based on empirical models, which are influenced by typical camera negative and print film rendering. In addition, we have some modern approaches, which are based on analytical color rendering. In the initial release of Baselight 5.0, Filmlight ships looks as cubes, which can be directly applied in T-Log. This will be an additional download from our website. The looks applied in T-Log with the Truelight Cam DRT downstream will produce a certain pleasing color reproduction. For example, we have a look that mimics the existing and widely used Truelight Film 1 DRT. Let's see how this works. We are seeing an ungraded shot rendered to sRGB with the Truelight Cam DRT. We can see a very clean image. I'm adding a layer now, set the layer number to 99, so it stays as my last layer in the stack. Now I'm changing one operator to Truelight. Once I have installed those looks, they will become available in this drop-down menu. And they are also to be applied in T-Log, so make sure that the stack color space is T-Log egamut. So for example, Truelight scene look film 1, this will match the appearance of this image as if you would have used the Truelight film 1 DRT. This is very handy. If we have started a grade, for example, using the Truelight film 1 DRT and need to deliver an HDR master, we are in a dead end, because the Truelight film 1 DRT limits us to a certain SDR range. Now we can use the TCAM DRT and this look to generate an HDR version of our grade, which looks similar to the SDR version, but with additional dynamic range. Truelight Classic, for example, is based on an analytical model and adds the needed treatment to skin tones and other parts of the color volume to change the default behavior of our pipeline to something very pleasing. Having a pleasing color reproduction as a separate process in the stack generates extreme flexibility for the colorist, as he or she can blend and combine different looks for different areas or for different sequences of the movie. Okay, that was a lot of infos. Just to summarize, the overall grading strategy in Baselight. Still, we convert everything to a common working color space and then use DRTs to produce our display-referred images. Now, with DRT families, the complexity for multi-deliverable projects is greatly reduced because the user picks just a DRT family and the actual DRT is selected by the system based on the viewing conditions. We have the mastering color space, which acts as a limiter to assure that nothing is encoded in our hard copy master we haven't seen while grading. And in the stack, in addition to all the new tools we ship in V5, we introduce a new working space for all the existing color grading tools, which should help to bring the existing tools into the new world of HDR cameras and displays. Truelight Scene Looks allows the user to change the pleasing color reproduction of the viewing pipeline in the stack. That's all for now. I hope it was informative and see you soon.